Morning. This is April 3rd, and our chapter is the Chapter 16 on Networks and Protocols. And this is kind of an overarching chapter on anything having to do with communications, and it really is more than this chapter can do justice to it. But that's why we, in the EET program, we require the students to take CSET 2200. So we hope to get this information more thoroughly into everybody in that course than in this course. So while we're interested in networks in this chapter, it's only to be used as a chapter to kind of get you a little bit into the idea of how to put a network together for PLCs, not an overarching chapter at all. We talk about protocols as well, and how to implement a protocol just a little bit, and how to set up beginnings of a protocol, and with a dire warning that they ain't easy, and because they go down a wire and they're serial communications, they're hard to see. And you can see them using various trapping mechanisms, but for the poor person on in the factory, they many times are hard to diagnose. So as you go through this, you always have to think in terms of the poor person who's going to maintain these systems, how they're actually going to maintain them. So we have a little bit of history in this chapter as well, and one of the things we want to talk about is the network for I/O that was used maybe 20 years ago, maybe 10 years ago, but it's probably fallen out of use in most applications today. New applications do not use Devicenet, but they may, but probably not today. But you may find these still active in a factory. They were very popular, and 20 years ago when we were buying our equipment in that era, we used Devicenet, and we made the students put together a network and get it up and running. And we made it with both the SLC processor and the compact logic processor. So while this is on the wane today, it could have at one time been something that you would have had high interest in, and even today you might have some interest in it because you may be walking into a situation where there is their Devicenet. So what is Devicenet? Well, it's a system of I/O devices that work on a 4-wire network, and it has its origins in a product that was invented for the automotive industry by the company Bosch, B-O-S-C-H, a German company, and it was used to develop a control mechanism for programming of devices in a car. And the rationale for using it in industry is because if you use these chips in cars, they're cheap because they make so many of them. So they're looking for, in industry, always a way to get the numbers up so that you can make a bunch instead of just a few. And CAN bus was the way to go. So CAN bus with an extra little twist is Devicenet, and CAN bus is a master-slave network that can run at different speeds, and it can be used in an automobile, and it has 2 wires for power and 2 wires for the bus, the serial communication, and the idea is very simple, but yet it's very profound in that you can really replace a lot of expensive wiring harnesses in a car with it. So there is some software that we did have at one time and probably still have licensing to, but we don't use it anymore. It's called RS Networks for Devicenet, and this RS Networks allowed us to set up a Devicenet network and then start using that in programming. So you would use the Devicenet network to set up the I/O, then you would start your program in your PLC, and that's what we see here is the SLC 503 and adding I/O devices, and then in the Compact Logic processor doing the same thing. The difference between the SLC processor and the Compact Logic processor was you had to create a file, a separate file that then you uploaded to the RS Logic 5000 program. So this program required an external file from that was created by RS Networks, and that file had to be created. So that's the only difference. SLC processors set it up without that extra file. Compact Logics used that file. And the I/O was set up, everything was based on an 8-bit byte, so every device at least took 8 bits, and that meant that you had 1 bit for the on or off status of the device many times, like a photo eye or something like that. And yet you had those other 7 bits, and this was a time when we were starting to think in terms of what can you do with those other 7 bits? Well, those other 7 bits many times were used to convey other information, like you're on but you're barely on, you're off but you're almost on, those kind of things. And that was part of the inclination toward making devices smarter. So while we didn't bring them in as an analog device, we did have more than 1 bit for each of these devices. So again, it was a step in the right direction. These devices sort of kind of have fallen from prominence. So and I also brought another thing up in this chapter, and that is the idea of control flash. You may or may not have gotten the opportunity to bring a processor out of the box and program it for the first time, but with Siemens, they take off and run. They may be a version that you might have to eventually upgrade the firmware on, but they will run. Allen Bradley does not. You must, from the very beginning, find that processor and flash it with a version of software. And we're on 31 right now, but we might be moving to 32, but I think there's 35 or 36 already out there. So again, this is something that you may or may not have done before, but please do not be, if you do get new equipment out of the box with Allen Bradley, this is something you must do. And it's not hard. It's just hook it up and let it go. And it's very, very easy to use, but it's just something you need to know. Okay, so when you're communicating with other devices from a program controller, you may use serial communication. You don't have to, but it's possible. The front end of the SLC processor had 2 9-pin ports on it, and one was used for programming to the computer. One was used to program to another computer, or you could use it and you could turn it around and use it as a read-write ASCII device. So we did have a lab that allowed you to do that, and this is the way that was done. That other channel was used, was turned into a user channel, and then you were allowed to set up the I/O, set up the baud rate, the data block, the whole 9 yards you were able to set up through this. And then you were able to do reads and writes with ASCII communications files. And you say, well, where did that come from? Well, this was a string, create a new, and then you would create an ASCII file, or string or ASCII file. Something you probably will not do, but you could run into this, and I wanted to bring this up, that you can actually communicate out the front of a PLC using that. Now you say, well, can Siemens do the same thing? And the answer is yes. We actually purchased with the first round of the Siemens an ASCII card that you can put on the left side of the processor, and it acted as a smart device, and you could actually do a communication, an ASCII string communication, and these are very valuable. and you can use them to set up, and you can even set up a specific protocol, and some of them are already given to you by Siemens. That's where some of these function blocks come in, because some of those function blocks are actually protocol blocks. So you can use ASCII characters streaming out the front end of a program controller. And you say, well, what does that mean? Well, this is an ASCII oscilloscope string, and you can look and see what they are. So you can actually see it on an oscilloscope. There are other ways of trapping ASCII communications, and there's boxes that you can put in the middle, or software packages that you can use to show an ASCII string going out of your computer or the program controller. There is a lot of different protocols, and one of them is the Modbus Protocol. We're going to talk a little bit more about it later, but this would be one of those, okay? These are the ASCII characters, and I'm sure you've seen those before. Here's a simple ASCII protocol, and this would be for a Pepperell and Fuchs RFID head, and this was something that was done about 20 years ago by myself. And you would say, okay, the character A, then the head number, and the checksum, and an ETX, end of text. And the response would be back a status, and it would be able to read all the data in the auto mode with a read head of 1. So this would be a example of a command, and then be able to read the information back. I'll give you an example later on as to why this is kind of a dangerous process to do, and this was not a good one, but there are other ones with RFID that we have that work very, 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 very well, and we do have a lab on RFID at the end of this chapter, which I'll introduce to you later. How do you create a checksum? Well, there's basically 2 ways. One would be add up all the hexadecimal numbers and strip away the overflow, or in other words, the carry out, and this would be your checksum. The other way of doing a checksum would be if you were to take this number and take its 2's complement, and then it would be that this number plus the 2's complement would give you the answer of 0. So it's either the addition or the 2's complement of the addition. That would be the checksum. Either way, it's easy to calculate. There are other checking mechanisms that are not as easy to calculate, and the LRC is the one that's the more difficult one. Okay, so how would you test a system that has RS-232 cables between them? Here is an example of a program that you would actually write. You communicate from one to the other. Here would be your ASCII write, and you can have a program. You can actually use an oscilloscope. You can have a program that reads the information, or there is also a breakout box. So any of these devices are useful for determining, is that information being transmitted correctly? In other words, is my output port working, or is it not? That said, this is something that when you hand it to an electrician or somebody who is not as competent, you may find that they have a hard time using this. Okay, so we want to talk a little bit about the Modbus Protocol, because it is a more robust protocol than the one I just talked about, and it does give you a lot of good results. And here is a description of this. Now, this was invented in the late 1970s. It was the first program controller protocol, and it was a master-slave protocol. In the early 80s, Alan Bradley came along with Data Highway, and then later on Data Highway Plus. And one of the reasons that Allen Bradley was able to overtake Modicon was because the Allen Bradley Data Highway was a peer-to-peer network, not a master-slave network. And with a master-slave, you had to worry about the master always being in control, and writing that software was not easy. So you had to have a computer, it had to sit there, and it had to be able to talk between the programmable controllers. It could be done, but it was not easy. On the other hand, the Data Highway Protocol was not hard, and it could be set up by most engineers, and you could get it to work. In other words, I'm a programmable controller, and I want to talk to another programmable controller. All I have to do is to do a get or a put, and then I could get that information. It was slow, but it worked. And there really were two things that caused Allen Bradley to overtake Modicon. One was just the mere fact that Gould had bought Modicon, and they were not a good master. They were not a good company that really cared about the companies that they bought, and they tried to milk them dry. Is what it boiled down to. The other one was Data Highway, and Allen Bradley had it, and Modicon didn't, and Modicon suffered as a result of that change. And if that had not happened, if Gould had let Modicon develop their Modbus Plus, which came along about 10 years later after the change had occurred between the two, if Modicon would have had that capability over that 10-year period from the early 80s to the early 90s, we would have seen a different dynamic between these two companies. And I think Modicon would still been a major contributor, although I don't really know. But it didn't happen. And the difference was this Modbus, and then historically Data Highway took over and basically ruled. The other thing that Allen Bradley had was they had the 1771 I/O architecture, which was a little bit more, I hate to use the word robust, it wasn't more robust, but it was a little less expensive, and it worked. And people set about to make up every kind of interface card that was necessary in order to interface a program controller to any other device in the world. And at one time, I heard that there was over 300 different I/O cards that did various things that were specifically tied to the 1771 I/O. In other words, you could plug this card into the Allen Bradley rack and it would work. And it was a third-party card. I'm sure they had to get permissions and all that kind of stuff and sign documents, but basically Allen Bradley let these people come on board and do various things, such as scale interfaces, such as PID interfaces, all kinds of things, resolvers, anything and everything was done with the idea that, you know, y'all come on board and we'll help you. And basically from the early 80s to the early 90s, Allen Bradley stretched and really did sell a lot of cards, and a lot of them were their own I/O, but they also sold a lot of third-party cards. So there's a lot of development going on in the I/O range, and that's where they actually mopped up. A little bit of history, but again. So we do want to cover this Modbus protocol just for a little bit, however, because it does have with it some very interesting capabilities, and I do want to talk to you about it, because while you say, well, I'll never use this because it was done in the 1970s, you may, and I had pretty much forgotten about it, but I was doing a job in 2007, and it popped up again. And the way that it popped up was there was a system that had three Merrick, M-E-R-R-I-C-K, loss and weight feeders. So this was a system that was a batching system of sorts, where they had three large bins and loss and weight feeders on those bins. And if you remember from chapter 13, the picture of the loss and weight feeders that were feeding a belt, well, that's exactly what we had. We had three large bins, and these were big bins. And it was a green project in the sense that we were taking something that was not nice and redoing it in chemical action and getting it to something that was not bad, and then using that product. The product that was the bad stuff was a byproduct of the steel industry, and when you make steel, there are products that go up the stack that are bad, and they're isotopes of chrome, and they stick inside the bag, and this dust residue that's in these bag houses has to be stored, and it can never be thrown away and just put out in the landfill. It has to be stored in 55-gallon drums, plastic 55-gallon drums, and those 55-gallon drums have to be stored, as you would say, in perpetuity, never to be released to the atmosphere. Now, you could pick it up, and it's not poisonous, it's not going to kill you, but long exposure to it does have an adverse effect because of these isotopes. So basically, you cannot put it into a landfill. You cannot get rid of it. So this process was one of an idea from a chemist, and it came in as a process that they patented, but then it was taken over later on by a steel company, and it was put in LaPorte, Indiana. So this process was a recovery process for this dust in these barrels. So what they did was they brought this dust in and they put it in this bin. They also had another bin with sand in it and another bin with old glass cullet. And they basically mixed these with a ratio, and then they put them into a furnace, which is a small glass furnace, and they were not trying to make glass you could see through. They were not trying to make anything perfect, but what they were trying to do was to get the isotopes of chrome to oxidize, which they did at the temperature of the glass furnace. These products attached an oxygen or O2 or whatever to the chrome, and so what had been a bad thing now became rust, an inert thing. So that's how this process was being done. But these loss and weight feeders we had to be able to control from an Allen Bradley program controller. And the way that that was done was through a box called Unibus. So we had Data Highway Plus, which was the high-speed I/O connectivity going out from the Allen Bradley, and it went to a box called Unibus, little black box, and out the other side of the Unibus was a control RS-232 cable, and there were three of these cables that went out to these three Merrick, M-E-R-R-I-C-K, control boxes, and the Merricks were using Modbus Protocol. So they were the slaves, we were the master, but we had to be able to read and write this information. Now, in this case, the only thing you really need to know is that there is a protocol, and there's a query and a response. And most of the time I'd ask you to be able to do one of these, and you can look at the problems in this chapter and you'll see exactly what I'm talking about. But I want to give you an example here, and we're going to talk through it, and that's all I'm going to do in this course this time, realizing that if you ever do have to do this, this book is available, and you can use this at your leisure to go back and make sure that you can actually build this protocol. It's not hard, but there's some tricks to it. And the trick basically is that the I/O starts numbering at 1 and not at 0. That was Modicon. Modicon starts their addressing in an area of a file at 1. So the first item in a file would be number 1, not number 0. That said, then everything is just an offset from the number 1. So this example is a query, function O2, which is a reading of input bits. So we go down here to the starting address. Again, this is in hex. C is 12 times 16, I believe, is 192, plus 4 is 196. But this is an offset from 1. So we're going to start our query at address 197. So the key is offset hex from 1. And that picks this off. Now we say, how many points do we have? Well, is this 16 points? No, this is 22 points because, again, this is in hexadecimal. So 16 plus 6 is 22. So I want to get 22 points starting at address 197. So I come down here and I look at this area, 197, 198, 199, 200, 201, 202, and there's a 1 in front of it. Basically, you can strip that off because these are the addresses I'm looking at, 197, 198, 199, 200. And you know I'm asking for 22. Well, here's 4, here's 8, 12, 16, 20, 21, 22. These I didn't ask for, and they could be 1s or 0s. I don't care. We basically say I didn't ask for them. I don't want them. Put them in as 0s. So basically what we have to do then is we have to look at these and say, now, these are a snapshot in time. In other words, I asked, and at that instant that I asked, these are what they are. In a second, they could all change. They could not change. We don't really care. This is not a continuum of looking. This is a one-time picture of what those bits are. So we look at it, and the first response would be this, A, C. The next response would be D, B. The next response would be 3, 5. And we come back up here and we look at the response. There it is, A, C, D, B, 3, 5. And then this thing called an LRC or a CRC. If you pick the one type, it's CRC. If you pick the other type, it's LRC. The LRC is the most robust because everything works twice as fast. But you decide how you're going to do that. That's not the hard part. The hard part is setting up the data so that when you're looking at an area that you get that offset from 1. So if I were looking at information from that scale, for instance, these bits mean something. Is it on? Is it active? Is it this? Is it that? Is it something else? I can also use one of these functions to set bits. I can also use one of these functions to look at words, 16-bit words that are coming back. I can also use one of these functions, a different function, but I can use one of them to write to a specific location. So again, these functions, there's over 100 of these functions, and I just show you 2 of them. But that said, this is all it is. It's a protocol that uses an offset from 1, not 0, but 1. That said, I'm going to go on. This is not hard. It just does show you, however, the idea of how this is done. So, you say, again, this is from the 1970s? Yes. But still used. And I can almost guarantee you that you walk into an application today, if there's this kind of communication, somebody's still going to use this Modicon protocol because it's one of the, even though Modicon isn't around much anymore, their protocols stayed this test of time because it was a very robust protocol with an offset from 1. Okay. By the way, I set that protocol up on a table in Toledo before we took it to LaPorte, got it working because I knew about that idea of that offset. I tried it out and it worked here, and then I took it out there and it worked there. It never had a hiccup, and I don't think they ever really had any problems with it. So again, knowing, having done it before was a big help. So I also want to be able to communicate from one program controller to another program controller. With the old Allen Bradley, it was a MSG or message block. Today, it is a get or a put. In most cases, Siemens uses gets and puts, and you can put two program controllers and talking back and forth, networking them together using get and put instruction, just like this, except that this doesn't look exactly like this because it's a Siemens instead of an Allen Bradley, so it does the same thing. So message blocks within Allen Bradley, gets and puts within Siemens. You can communicate PLC to PLC. Not hard, it's done. And why would you do that? Well, you would do that because you want to split the load between more than one processor. You have part of the action going on over here, you have part of the action going over there. They have to communicate back and forth. Well, you do it with this MSG or gets and puts. Now we want to talk just a little bit about the industrial network, the different types, the types of industrial networks. And the reason for doing this is because there is the things to be careful for. And one of the things that you can definitely do is to overextend your network. We talk about in Chapter 18 about too many interrupts. Well, in Chapter 16 we can talk about overextending your network and not having enough bandwidth to be able to accommodate all the things you need to do. That said, this is, I mean, I don't have all the answers to that, but here's some of the names that you might be interested in, okay? So, what are these things? Well, Profinet is what you use for Siemens in most of the European standards. Ethernet IP is what you'd use for the Allen Bradley, the high-speed Allen Bradley. Now, these are both Ethernet. They both work on Ethernet, but Ethernet IP has an extra chip in the system. It's proprietary to Allen Bradley. So this really is a proprietary network. This really is an open network. That's something different than what you would probably think, because you probably think, well, this is something the Germans have tied down, and this is something that's open. It's just the reverse, but they both work, and I don't want you thinking that, well, one's better than the other because of that. They're both out there, and they both work. So don't, and they both work on an Ethernet cable. Here are some of the various network capabilities, and I've got Profinet, Devicenet, Ethernet IP. Ethernet IP is the one we just talked about from Allen Bradley. Devicenet is the lower speed one. Here's some other ones: Field Bus, Foundation Field Bus, Modbus, Modbus TCP, and EtherCAT. But again, I don't want to confuse you. These are just some names. Now, where did these blocks come from? This is from a school that I went to about 10 years ago at in Detroit, or a suburb of Detroit, that basically was an introduction to Profinet, and it was a one-day seminar, and I just took some of these slides and I redone them a little bit, but basically this is some of the difference. Now, Profibus was the older network. This was the 9-pin cable. This is the Ethernet cable. So everything now is done with Profinet. Now, how do you care about these two? Well, I'm not so interested in these different layers as I am about what does it take to get high speed, and that's what I really want you to concentrate on. So here's a picture of the different speeds, the different layers of speeds that you can have. So for programming, just use this one, configuration. Real time is this right here. This would be your regular I/O. Here is your high-speed I/O, and here is motion control. You say, well, what's the difference? Well, configuration would be as is. I mean, you can just let it go. Here, you have to answer within 10 milliseconds. High-speed I/O within probably about 1 or 2 milliseconds. Here, you have to guarantee sub 1 millisecond I/O turnaround. So it goes from don't care to care a lot. And these are all under Profinet, but they're all different layers, and you have to configure these differently. If you were to configure some of these other ones, which we don't do, if you were to do these, you would have to do special configurations so that you get them to work according to what you need. If you do motion control between processors, you really have to be careful, and this is the one that probably the most difficult to do. There are other networks other than Profinet and Ethernet IP. So we talked about Devicenet up there before. Now this is the European versions, and you can have straight digital I/O, or you can have what they have now is called Ascii. And Ascii is a equivalent of Devicenet, although it works at a higher speed. So Devicenet, while it may have kind of gone away, is not totally gone away, and you can have the competitive one is Ascii, A-S-I. It's said as Ascii. Okay, so what do you have to worry about? Okay. Well, I was talking about that RFID, and here's what I did, and here's what happened. Okay, so that RFID reader that we've talked about at the very top of the chapter, this is what actually happened. The programs were in the processor. Then there was a remote I/O processor that was it was in the I/O rack of the Allen Bradley. Then there was a vendor remote I/O receiver module that basically read this information. Then there was a vendor communications block that communicated to 4 RFID readers, RFID tags, and then we had the physical tags. Now what happens when you have 4 computers talking to each other, and the communications went bing, 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 and then bing, bing, bing? Well, I'll tell you what happened. If you start a communication and then you start a second communication before you've received the information back of the prior communication, this one hung up and it would not restart. And in order to restart these, you had to physically go out and power this one down. Turn the power off, turn the power back on, and then it would come back. So you say, well, how did that ever happen? Well, I tried this system out on on my desk. It worked. I had it working 100%. Took it to the field, and I used a prox switch to initiate the communication. Prox switches are very noisy devices, so when the device came in on, this was a system of like a merry-go-round of stations. There were like 16 stations, 18 stations, and that type of thing. But anyway, there were enough stations that the device would, the pallet would come in, hit the prox switch, and then you would read the RFID tag, and then you would write to it something or whatever. Well, in that process, I learned that these proximity switches were noisy and would initiate the communication and then would initiate it again. So what I hadn't done was seal out the second communication until the first communication came back with a done bit. It worked on the bench, didn't work in the real world, and this guy tied up. And it took me a while to figure it out. It did eventually, but as you would think, this was not very good. So again, it eventually worked, but this was not a good system. And I would repeat to you that this was an old, very early version of RFID. It was done in 1998, 22 years ago. But this is not the way to do it. Guaranteed you that was not the way to do it. So we get down to something that's a little bit more interesting. This is a picture from a movie, and maybe you recognize these two guys. This is Strother Martin, not somebody you probably ever recognize. This is Paul Newman, somebody you probably would recognize. And this is the movie Cool Hand Luke. I think it won the Academy Award for Best Movie in 1968, or in that range, 67, 68. I don't remember the year, but I actually saw this when I was in college, so that tells you how old I am. But very interesting statement from this guy right here. It says, what we have here is a failure to communicate. But he didn't say it that way. He said, what we have here is a failure to communicate. He cut it off, but anyway. So that's not what you want to do. You want to have a system that does do communications correctly. And there's several labs in this course that we're going to talk about. And at some point in a book like this, you think, well, we ought to talk a lot about Factory 4.0 or Industry 4.0. Yes, we should. And one of these days we will. This is just an attempt to say it's a subject that we ought to think about and start planning for more than we have in the past. So I know that it's there. I know that it's something that we need to consider. But it would go in this chapter probably as much as anywhere, or maybe in chapter 21 on AI. But the exercises at the end of this chapter are having to do with talking about the Modbus Protocol. And this is Devicenet, setting up Devicenet. But these right down here are questions on reading of the Modbus query. So you might be interested in trying some of these. Be my guest. This is not something that I expect you to do on a test. I would have, and if you look at the old tests, this was something that was always there. But I'm not going to press that in this semester. But at least please recognize the thought that if you ever run into this, you can go back and review it and make your life a lot simpler, for the simple reason that I don't want you to have to stumble over that Modbus protocol. I don't want you to fear it. It's not that hard. There's some tricks. You can do them. And I also want to talk about the labs. Okay. In this course, we had really haven't moved it into this chapter as much as I just give you the information and let you do it. But there's an RF200 system from Siemens, and here's two YouTube videos, or not YouTube, but Siemens videos to support it. Really 3 videos that support it. So with that, there's tags there's 8 tubs that have tags and these controllers, these RF200 controllers, and you can add those to the left side of your S7-1200s, and then you can do the RFID communication, and you can read and write to these tags. These are the help screens to allow you to do that. Or you can write between 2 PLCs, do a communication between 2 PLCs using Ethernet, and you can do this with either Allen Bradley or Siemens. And that gives you the idea that you can communicate between 2 of them. Or you can take the Ascii Protocol communication protocol and attach it to the left side of the Siemens processors, and then you can talk ASCII between 2 devices. Any of these 3 are available. You can put them together and get them to work. Hopefully that helps. There's a lot here. Take care.